Greetings, this is Mrs. Radigan with a lesson on graphs of rational functions. Remember, a rational function is just a function that is written as a fraction. So we have a polynomial in the numerator and a polynomial in the denominator. When we graph rational functions, if you remember from last year, we have to start by factoring the numerator and the denominator. And then we find all of the critical points. Those include the roots or the x-intercepts. So we set the numerator factors equal to 0 and solve for x, and we write those as ordered pairs, some x value comma 0. Then we find the discontinuities. We have removable discontinuities or holes that we find as factors of both the numerator and the denominator. We set those factors equal to 0. We find the x value, and then we substitute that x value back into the simplified function to find the y value of the whole. We state those as ordered pairs. The other type of discontinuities are the non-removable. Those are the factors that appear only in the denominator, and we set those equal to 0 and write those as vertical lines, x equals some number. Then we look for the x or the y-intercepts, so we set x equal to 0 or plug 0 in for x and solve for y. We state those as an ordered pair, 0 comma some value that we found. Then we look for the end behavior of the function. So when the degree on the highest exponent in the numerator is less than the degree of the highest exponent in the denominator, we get something like 1 over x, and we end up with a horizontal asymptote at y equals 0. If we have equal degrees in the numerator and the denominator, like x over x or x squared over x squared, we get a horizontal asymptote that is equal to the ratio of the coefficients on those x terms. And if we get a degree that is larger in the numerator than the denominator, we did not do these last year, but we will this year, we get some type of slant asymptote or quadratic asymptote. Once we have all of that information, we go ahead and graph those points and lines. And then we create our sign patterns using our critical values, which are zeros and our roots and our vertical asymptotes. And we find the signs in between each of those values and to the left and right of them. From that, we pretty much have our entire function ready to graph. And we are then going to identify some other key attributes of the graph. We're going to talk about the end behavior in terms of the limits of the function. We're going to talk about where the function increases and where the function decreases. And then we're going to talk about concavity. So this is a picture of concavity. So this is concave down, the blue, and the red is concave up sections of the graph. Those places change concavity, or the graph changes concavity at what we call inflection points, but those are found using calculus, so we will just do our best to estimate those for now. We're going to start by finding the end behavior of some functions. So remember, we said end behavior, we're just looking at the highest degrees in the numerator and the denominator. So we have x squared over x cubed, which we can simplify to 1 over x. We said if the numerator has a degree less than the denominator, this ratio as we go to infinity, 1 over infinity or 1 over negative infinity, is going to get really close to 0. So if we look on our graph here, we see the ends are going to 0. And the way we write that is as limits is the limit as x approaches negative infinity of f of x is the same as the limit as x approaches positive infinity of f of x, because those are both heading toward the end here, 0. If we look at the next one, again, we're just looking at these highest degrees. We see that 3x squared over 5x squared simplifies to 3/5. So our end behavior model is y is approaching, or sorry, as x approaches infinity, the y is getting really close to this line of 3/5. So we say the limit as x approaches negative infinity of f of x is the same on the right side as x is approaching positive infinity of f of x, and that value is getting really close, we see on both ends, to 3/5. Now we're going to go ahead and graph some rational functions. Step 1 is to factor those, so we factor this function to these factors. We're first going to find our roots. We see that x minus 1 over x minus 1 is a removable discontinuity, so that will not be included in our roots. So our root here will be -3, 0. Our removable discontinuity is at 1. We're going to plug that into the simplified version, because if we plug it in here, we'll get a 0 in the denominator. So we're going to get 4/2, which is equal to 2. And that's going to be our hole in our graph. And then we see that our only vertical asymptote is the factor that does not cancel in the denominator, so x equals -1. Then we are going to plug 0 into our function, so 0 plus 0 minus 3 over 0 minus 1 is going to give us a y-intercept of 0, 3. And lastly, we're going to look at our end behavior. So we look at x squared over x squared, and that's going to give us a end behavior model of 1. So we have a horizontal asymptote at y equals 1. Now we're going to go ahead and graph all those critical values on our graph. So I have graphed the root of -3, 0. I have graphed the hole at 1, 2. I've graphed the vertical asymptote at -1, the y-intercept at 0, 3, and the end behavior at, or horizontal asymptote of y equals 1 here. Then we're going to go ahead and find our signs. So we don't need to include the y minus 1 because that would give us the same sign in the numerator and the denominator, so it wouldn't change anything. So we're just going to look at x plus 3 over x plus 1. If we plug in something smaller than -3, like -4, we're going to get a negative over a negative, so the sign would be positive, which means the graph lies above the x-axis here. Then between -3 and -1, like -2, we get a positive and a negative, so that would result in a negative y output. And something bigger than -1 would result in 2 positives, so we would get a positive output. So we go ahead and graph that, and we see that left of -3 we're above the x-axis. Then we start to go to a negative value of y. And then up here, we are all in the positive area, and we head towards 1 there. Okay, now we're going to find some attributes. So this function is always decreasing, so we have no increasing intervals. It is decreasing from -infinity up until -1. Then it is decreasing again from -1 to 1. Then we have a hole, and then it decreases from 1 to infinity. It is concave up here, so that's going to be the -1 to 1. And then it's concave down here, so that's going to be the -infinity to -1. Then we are going to look at our limit statements. So as x is approaching this vertical asymptote of -1 from the left side, so we write that the limit as x approaches -1 from the left of f of x, we see that it's going down to -infinity. as it approaches it from the right, so we say -1 approach from the right, when we look here, as it approaching it from the right, it's going to positive infinity. And then our last one, the limit is what happens at the end. So as x is going to negative infinity and positive infinity, y is getting closer to 1. And so we write our end behavior limit statement as f of x as x approaches negative infinity and positive infinity, the function approaches 1. Okay, we'll go ahead and graph one more function. I've gone ahead and factored that. So we see that there are no removable discontinuities, so that means both of the numerator values are roots. So we have -3, 0 and 2, 0 as our roots. We have a vertical asymptote at x equals 1. If we plug in 0 to the function, we get 0 plus 0 minus 6 over 0 minus 1. So our y-intercept is 0, 6. And then if we look at the end behavior x squared over x, we see that that simplifies to x, but we can actually find a more exact end behavior model by doing some division of x squared plus x minus 6 over x minus 1. The easiest way to do that is to use synthetic division. So I'm going to use 1, 1, negative 6 as my coefficients on my dividend, and then my divisor, x minus 1, I'm going to put the 1 here. So as always with synthetic division, we drop down our first one, we multiply and we add, we multiply and we add. So we actually find out that the end behavior model is actually y equals x plus 2 from the synthetic division. So because this end behavior model is a line, we actually have no horizontal asymptote on this, just a diagonal slant asymptote. So I'm going to go ahead and graph these critical values and lines. So I've gone ahead and graphed the x-intercepts, the vertical asymptote, the y-intercept, and then our end behavior model of y equals x plus 2. We can go ahead and use our signs to find where the function is positive and negative. So if we plug in a number smaller than -3, like -4 to all of these factors, we get a negative, a negative, a negative. So that makes 3 negatives. Something in between, like 0, we get a positive, a negative, and a negative. So that makes a positive. Something like 1.5, we get a positive, a negative, and a positive. So we have a negative, and bigger than 2, we're going to get all positives. So we know our function is negative and has to hug this left of -3. Then it becomes positive as it goes between -3 and 1. And then it goes back to negative and then crosses through to the positive part of the graph. We can then see it's always increasing, never decreasing. So we go ahead and write our increasing intervals from -infinity to 1, and then 1 to infinity with no decreasing intervals. It is concave up here and concave down over here. So we write those intervals. And last, we write our limit statements. So as we approach 1 from the left, we're going to positive infinity. As we approach 1 from the right, we go to negative infinity. And on the ends, we're going to negative infinity when we're going toward negative x, and positive infinity, we're going to positive x. So the limit as x approaches 1 from the left is positive infinity, and from the right is negative infinity. As x is going to negative infinity, y is also going to negative infinity, so there's half of our end behavior limit. And on the right end, it's